Welcome everyone to another evening with the Berlin Functional Programming Group. I haven't done one of these in a couple weeks, but I do have more talks coming up this fall, and I'm already thinking ahead to the spring. I originally started doing this back in April or May, I don't even remember, basically as a way of improving the morale of the functional programming community during the pandemic, and helping myself and helping everybody else get through it by meeting interesting people from around the functional programming world and having them come to us virtually. Since we can't meet each other in person, we might as well take advantage of the so-called global village, which is what we called the internet in the 1980s. Before we begin, just a few links for you in the chat, as usual. If you'd like to buy an extremely attractive Berlin Functional Programming Group t-shirt, they're available on Teespring. You can follow us on Twitter if you don't already. We have a YouTube channel. As a reminder, this talk is being recorded and you can look at it on YouTube later. We also have a channel in the FP chat Slack group if you would like to find us there. And finally, if everybody who is in the meetup now can just type into the chat, where are you from? I think our speaker might be interested to see where in the world everyone is joining us tonight from. I would too. Berlin, London, Berlin, Brazil, Belgium. Oh, cool, a lot of people, California. Oh, hi, Vlad. A lot of people from a lot of different places. So I am pleased to introduce to you, I'm going to try to pronounce his name, Gergő Érdi. Gergő's work came to my attention when I was looking at a, I think a Haskell weekly newsletter email that I got, and I just saw the mention of text adventure games and Scott Adams, and this immediately brought me back to 1984. And this is kind of where I cut my teeth on computers, and probably how I got into programming. I wanted to make my own text adventure games, and the combination of text adventure games with Haskell hooked me, and I had to ask him if he would be so kind as to prepare a talk for us. And miraculously, he agreed. And the miracle is not that he would agree to talk to us, but that he would join us from Singapore, which is in a very inconvenient time zone for talking to anybody in Berlin. So I really appreciate that he has agreed to join us, and I'm very much looking forward to this talk. I have no idea what we're in store for, but I think it's going to be great. And Gergő, I'm going to put the spotlight on you, and the floor is yours. If you have questions, please type them into chat, and I will give you a chance to unmute and ask them when there is an opportunity for that.
So yeah, thank you. So thank you, Stephen, for inviting me. Of course, that also means that the responsibility falls on your shoulders if the talk turns out to be not so interesting. So then you're to blame. So
I'm totally willing to take this blame if necessary.
Okay, so hopefully my slides are now shared. You can see my slides, right?
Yep, looks good.
Okay, so hi everyone. So my name is Gergő Érdi, and I'm going to talk about Scott check, which, well, we will see what it is. I'm not going to tell you up front what it is because we need to get there via a somewhat meandering path through text adventure games, symbolic execution, and SMT solvers. So let's get to it. So first of all, let's talk. Oh, I can't change slides. Okay, so first of all, let's talk about adventure games. What are they? What do they look like? What do they look like on the inside? And how would you make a software implementation of an adventure game? So for those of you who don't know what text adventure games are, so these are a couple of screenshots. The top left one is Colossal Cave. So this was the original text adventure game from I think like early 70s. It ran on main, well, like PDP 11s of the time. So what you see here, of course, is a present-day Linux terminal running a version of it. And then the top right one is running a Scott Adams adventure game, which will be of particular interest to us in this talk. We'll see why. So that one again is running on a modern Linux machine. The one on the bottom left is a Commodore 64 text adventure game. Now, I'm pretty sure that this is closer to Stephen's experiences with text adventure games. But this one in particular is a Hungarian text adventure game, which was the first commercial quality and actually sold for money text adventure game that was in Hungarian. And then on the bottom right, you can see a reverse engineering based rewrite of this game running in a modern environment. So I did this one. So what, like 5 years ago or something, I sat down and with a Commodore 64 emulator and a monitor and started disassembling the program just to be able to extract all the data out of it so that I can then re-implement it in a modern interactive fiction authoring environment to, in that sense, keep it for posterity. So text adventure games are basically a subset of interactive fiction. So interactive fiction means that there's some textual back and forth between the user and the computer. And this is a very vague definition. So, and that's intended because there are lots of strange things that people have made under the interactive fiction label. And for example, for those of you who know ELIZA, right, which is this conversation simulator that was, I guess, popularized by having been included in Emacs since very early versions. So it's one where it acts as your psychologist and you type something and then it asks follow-up questions. But of course, it's based on very simple textual manipulation rules. So some people would classify that as interactive fiction. But we're going to talk about text adventure games, which are a subset that are proper games. So I would say that the difference between an interactive fiction, or like in general, the difference between a toy and the game is that the game has a well-defined win state. So if you play a text adventure game, what you're doing is usually that the computer is simulating some kind of environment. You are controlling like an agent in that environment, and you have a goal, and you're trying to manipulate your environment to achieve that goal. And while I was preparing for this talk, and when I was doing my first slide about the definition of text adventure games, I realized that by this definition, when I was installing Debian Linux 2.0 back in 1998, it would be very difficult to prove that I was not playing a text adventure game because it was happening over a textual interface. There was a lot of back and forth between the computer and me, believe that. And I did have a goal in mind. And because I was installing from a CD, so that it was not connected to the outside world, right? It wasn't connected to the internet. It wasn't connected to anyone else. So how was that different from playing a game that takes place on your computer? I don't know. But I would say that that wasn't an adventure game. But yeah, so it's a bit nebulous, this concept, but I guess you know it when you see it. So why can't okay? So and then, but one important thing that follows from something being a game is that if you can't win that game, then the game is faulty. So it's very frustrating for a player to start playing a game thinking that he can achieve a given win state, but it turns out that no matter what he does, he can't get there. So this is the property that we're going to try to check. So what we're going to be talking about here is taking a text adventure game and making sure that it has a solution. And we're going to do this check constructively, in the sense of we're going to basically try to find a solution. So we're going to try to find a sequence of user inputs such that starting from the initial state of the game, we arrive at the win state. And I should add one more thing. So depending on the game design sensibilities, you might also want to rule out so-called dead man walking situations. So early text adventure games thought that it's fair play to allow the player to do something early on in the game that doesn't result in some obvious game over, but it makes the game unwinnable later. So like the Hitchhiker's Guide to the Galaxy text adventure game adaptation, I think, is famous for this. Like when you start the game, if you forget to pick up some item from Arthur Dent's home before it gets demolished by the Vogons, you know, nothing bad happens. You can keep playing the game, but much later you will have no way of progressing without having that item. And of course, you don't even know that you're supposed that if only you had that item, you could have done something with it, because, you know, you might not even remember, or you might not even realize that there was an item that you could have picked up. So this is out of scope for our work here, but I think it would be an interesting extension of this work to check not only that you can win a game, but also that you can't get to a state where it's not game over yet, but also there's no way to win anymore. Because in modern times, game designers usually want this property. So what makes text adventure games interesting from a technical point of view is that usually they are not ad hoc in terms of their programming. So what I mean by that is that the way most text adventure games are written is that there's a separation between game data, which contains the description of the simulated world, which has, you know, like static parts like locations and the map between, like how the various locations are connected, and, you know, the names of the items and the weight of the items and so on. And also there's some dynamic, that's like a scripting data. So this is the part that describes how the world reacts to various things. And then you have an interpreter which consumes this game data and presents it to the user and you know, runs it. So you would have many games that are all using the same interpreter, just different game data files. So you would, and this means that on one hand that you would have these whole families of games like Infocom, right, which was a I think MIT-based text adventure game studio. They had their own setup where they would basically have a virtual machine, and every Infocom game was compiled to run on that VM. So when you bought a game, what you get on the disk would be the same interpreter as you would get in the disk of another game, but then the game data was different. And this allowed them to port the interpreter to many platforms and thereby instantly get all their games running on all the platforms that they had interpreters on. And similar for ADS, I think I'm not sure it's called ADS. What's that called? Anyway, so there are several other engines. So Inform is interesting because that's a new wave system. So it was an open source system from the late 90s that was originally aiming to get the old Infocom games into new formats. So it's targeting the same VM, but it's a third-party language and compiler, which since then has been under active development. And the latest version of Inform, for example, is based on this. I think it's quite weird, but it's based on this natural language-looking syntax. So if you read an Inform 7 games source code, it almost reads like a literate programming file. But what looks like the literate programming comments is actually the source code. So then, for example, on the screenshots that I showed earlier, so that's why those ran on inside modern Linux terminals, because those interpreters were interpreters targeting modern computers that consume the same game data format that the old games were written in. And in particular, one company called Adventure International had this same setup where they had the game data and the interpreter. And this is the one that we are going to be looking at in this talk. So Adventure International was basically, originally it was just one guy. So it was Scott Adams, who has nothing to do with Dilbert. It's a different Scott Adams. So he created this system for text adventure games running on late 70s home computers, I think Apple II originally. So his games were very much a product of the constraints of this environment. So at that time, the large, complicated text adventure games ran on large, complicated, and expensive computers. And he was aiming small. So these games are much more regular, I would say, than the Infocom games. The scripting language is much simpler, and the structure of the games themselves, like narratively, they are very simple as well. So these are not good games. Okay, so I don't want to recommend anyone to play Scott Adams adventure games if we're being completely honest here. However, all this simplicity means that if we want to play around with interpreting and analyzing these games, this is a good starting point, because this is like the minimal viable text adventure engine that still has some real text adventure games from back in the day. So the way these games work is that in all of them, the goal of the game is to find treasure. So there are some items that are marked as treasure, and there's one location called the treasury. And of course, these are skinned according to the given game. So it might be that it's not called the treasury. It might be like the boat from which you go on a diving expedition to get sunken pirate treasure, right? So then the treasury would be the diving boat, and so on. But you basically, how you win is that you have this command called score, which shows you the number of treasure collected, and you win by issuing score when you have max score. So as soon as score reports that you have collected 15 out of 15 treasure, then you win. So the win condition is very well defined. It's very rigid. So all games have the same win condition. And the format of the game data itself is also a product of its environment. So it's a text file, because the interpreter originally was a basic program running on the Apple II. And the basic environment there didn't really support binary data. So what happens, and we look at the file in detail just to get an idea of how we would want to process it in a modern environment. But basically, it's just magic numbers, and the numbers are not, so like all the numbers are 16-bit numbers, because that's the number format that BASIC uses. But I mean, when I say BASIC, I mean the Apple II BASIC. And there might be like multiple pieces of data encoded in one of these ints by, I think in one of the cases, it's like modulo 200. So it's not even like bytes. So you take the number and you divide it by 200, and that gives you the number and the divisor and the remainder. And these two are the two smaller numbers that actually mean something, but because it could only be loaded and stored as a 16-bit number in a text format, Scott Adams put them together to save on space, both on the data file and also in memory while processing it. So there are lots of idiosyncrasies like that. So what we're going to do is we're going to look at this format, and then we're going to make in Haskell an interpreter for it, which allows us to play these games. Okay, so that's not really interesting so far. But then we're going to modify that to check that we can win a given game. So first of all, what do these files look like? So here's an example file. So first, there's a bunch of magic numbers, which is a header. So these describe the rest of the file, like, for example, the number of rooms and the starting room and so on. And then we have the dictionary. So each game comes with its own set of words that it understands. And the dictionary is split into two halves, the verbs and the nouns. And every input is parsed exactly into one verb or one verb and one noun. And the rest of the game refers to these words by their index. And the reason that you only see three-letter words here is basically to make the parser, the game parser, more resilient. So basically, if the user types in getting coins, it will be parsed just the same as if you just put in get coin, right? So this not only saves on memory, but also makes the parser appear somewhat smarter than it is. So then we have the static data. So these would be the rooms, where the first part, this part is the, actually, I hope you can see my mouse pointer. So this part is the connections between the rooms. So like room 1, if you go, I guess, south, you go to room 2. If you go north from room 2, you get to room 1. You get the idea. And these are the names of the rooms. And then we have the messages. So these are messages that will be referred to from the script. So these are just strings. And then we have the definition of the items. So the items are not necessarily things that you can carry around. The items are basically just things that you can interact with. They just appear in rooms. So each item has a starting room. So like the sign is in room 1. So when you go to room 1, it will say that there's a sign and it says leave the treasure here. So basically that's how the player knows that this is the treasury, right? And then some of these, like the cross or the key, have these markers for the word that can be used to refer to them. Like, so these are the ones that the user can pick up by saying, like, if you say get cross or get crow, that means the wooden cross, which is the second object. If the player is in room 2, you can pick up the cross, and now it's traveling together with the player, and then you can drop it in a different room. Okay, and then we get to the most interesting part for us, which is the script. So this is the encoding that I was saying, that there's like some modulo 200 and modulo 150 composite numbers, but each line basically corresponds to the user input, a set of conditions to be checked, and then a set of state changes. Now, how do we decode this? So the easy answer is we look at an existing interpreter. So there's an interpreter written in C called Scott-free. And that's open source. It's written by Alan Cox, who some of you might know as a prominent Linux kernel developer. So he wrote this, I don't know, decades ago. But it's like a small C program. You can compile it in modern environments. You can read it, and it's quite readable for a C program, I guess. And so if you look at that, that's how you figure out what all these magic numbers mean. So I'm just going to show you an example. So this line, the 757 encodes that this script should run if the user types open door, and then there's a condition. So two conditions actually. The first condition is that the logged door, which is item number 2, is in the current room. So that means that you can only open the door if you're in the same room as where the door is. And the second condition is that item number 3 is not available. So here, available means that it's either in possession of the player or it's in the same room. So if you're in the room and you have the key and you want to open the door and the door is there, and the door is, sorry, if you want to open the door but you don't have the key, so the key is not available, then the action is to print message number 2. And if we go back to the messages, we should get, yes, message number 2 says it's logged. Okay, makes sense, right? So before we move on to what we want to do with all this, so the rest of the talk is probably not going to make much sense if you don't have at least some vague idea based on all this what a text adventure game in scope roughly looks like. So maybe we should take any questions if there is any so far. Yeah, I can't easily suggest. So I'm going to assume that there are no questions unless the study.
Is there a problem?
Checking if there's any questions so far.
I don't see any questions. No, not yet.
Okay, cool. So then, okay, so moving on. So here's the plan for based on this. So prompted by Martin Lester's talk at the workshop on program rewriting for transformation and evaluation conference earlier this year. So he had this talk where he took Scott free. So this is this C interpreter for Scott Adams games. And so he basically partially evaluated it for a given game, but manually. So basically he took the source code and removed the part which loads this data file and parses it into Scott free's internal data structures. And instead he just filled in those data structures, like, initialize them to the right value based on a particular game. And then all the infinite loops were replaced with bounded ones. Because if you think about it, a text adventure game at its core is an infinite loop, right? It's an infinite loop of getting getting the next input from the user and then reacting to it and doing it over and over again. So he replaced all these with some sufficiently large bounded ones, and then passed it to CBMC. So CBMC is an off-the-shelf symbolic compiler. So basically it takes a C program and compiles it into an SMT problem. And we will go into what an SMT problem is. So basically puts it into symbolic form, which describes the behavior of this program without knowing what the inputs are going to be. And then passes it to an SMT solver, and then the SMT solver finds a set of inputs such that this symbolic description of the end state evaluates to a state that is a win state, right? So you have this C interpreter, you remove all the I/O from it, basically. You pass it to a very strange C compiler, and what comes out of that, you pass it to an SMT solver, and then the SMT solver will give you, if it can find a list of user inputs that win the game. So what we're going to look at here, so my plan was to replicate this with bubblegum and duct tape. So what I mean by that is I wanted to do this by starting with an idiomatic Haskell interpreter. So we're going to write the Haskell interpreter for the Scott Adams games. And then we're going to change it just so. So we're going to only change it a little bit to support symbolic evaluation and see what we need to change. Because I didn't know up front what we'll need to change compared to the normal interpreter. But we'll just let the type errors lead us. And also part of this bubblegum and duct tape approach is that everything you hear here was done in 1 week. So this was like a very short project, which, well, I guess it shows in some parts of the end result, as we'll see at the end. But so this was not like a large project. This was just seeing what we can quickly mash together to replicate, to do something that's in spirit similar to using an ascent over to win, to find the winning set of moves. So now that we know what adventure games look like and what we want to do, so let's first write an interpreter, a normal interpreter, an interactive interpreter. So how do we do this, right? So basically, the whole point is to do it exactly how anyone would want to do it in Haskell, right? So we are not really thinking ahead here in terms of symbolic evaluation. We just do the most straightforward things. So what is the most straightforward idiomatic Haskell approach to this? Well, first of all, we make some algebraic data type that contains the full description of a given game. So basically, all these, the header fields and all these string text messages and the script code, all this is represented nicely as a record. So you write a parser that produces this record. And then the state of the game. So on this slide, it's somewhat simplified. If we have time at the end, we can look at the real implementation. It's not really any, so like, okay, so because you have stuff like light sources, and you have to know how much oil you have left in your lamp, and because some games have dark parts, and you have to be stingy with your oil usage and stuff like that. But the core, the essence of the game has only two states. So one is the current room that the player is in, and the other one is where each item is. So as you see, I use int16s because that's what the original game uses. So it's a bit overkill because, like I said, there are some parts of the script, some parts of the data file where like parts of the script are actually stored as int16s, but it can be taken apart into much smaller numbers, but it doesn't really change anything. So we'll just go with the simplest thing and put everything in an int16. So current room is the index of a room, so it's a number. Item locations is an array where, because we know how many items there are up front, the only thing that can change is values in this array. Okay, and then how do we do the interpreter? Well, we just use the good old RWS monad stack, right? So we have a reader is the one, like in the reader we contain the game data. In the state, we have the state, the game state, and then the writer collects a list of string, which is the output of the game in a given turn. So if we want to make one step of game, like if you want to run the game for one step, what we do is we supply the parsed verb and noun numbers. So these are the two int16s. And then we get back a maybe bool running inside this RWS monad stack. And the maybe bool is basically, it's nothing if there's no end state yet. and if it's just a bool, then it returns whether we have won or not. So if it's just true, then we have won. If it's just false, then we have finished with a game over, like a fail state. And if nothing, we should keep playing. And of course, you might ask, why am I using reader T, writer T, and state separately instead of using an RWS? So we'll see later on that it will just, there's like going to be one tiny thing that is simpler if we do them layer by layer. The reason for that is that there's going to be one point where we want to peel off only reader T and writer T, but keep state. So I thought it's easier if we, even in the interactive interpreter, we do it like this, because then there are less things to change once we get to the symbolic version. And then, of course, the last part is that we have this thin layer of I/O that drives the whole thing. So, you know, well, I didn't write it here, but of course, the first thing that the I/O layer does is it reads the game data file and passes it to the parser. Okay, and then the parsed game data, it initializes the engine, and then it gets into this loop of getting user input, parsing it with the dictionaries in the game data, and then passing it to this step function. And then the list of strings that comes out in the writer is printed to the output, and then we start again with the input. Right? So this is, you know, there's nothing, like there's deliberately nothing interesting in this part. Because that's the whole point. I wanted to see what happens if we start with a normal Haskell code and then try to make it, you know, try to change that to use symbolic evaluation. Any questions so far? Okay, now I can see the chat and I see that there's no questions there. Okay, cool. So how are we going to find the solution to the game, right? So if you think about it, if we have this dictionary of even just 20 verbs and 20 nouns, that means that we have 400 possible inputs at every step. And if the game takes many steps, of course, it's going to exponentially increase in size. So if we were just blindly trying out inputs just to see what would stick. So we want to do something smarter. So this is the tool we're going to use for this is SMT solver. So now I'm going to introduce what those are for those of you who are not familiar. So what we want to do, right, is we want to find an input such that if we pass it to this step function, and then we take the end state of this step, and then we pass the second input to this step function, and then we take the end state of that and pass the third input, and so on. So then the final state, which of course is only final because we have decided that we don't need any more input. So let's say we have an input of 5 lines. So then the 5th iteration of this thing should return a just true, right? So how are we going to find an input that satisfies this constraint that after folding it over the, folding the state over this input, we get just true. So the basic tool for this that we're going to use is the Boolean Satisfiability problem, which is also called SAT for short for satisfiability. So basically, the SAT problem is that given a Boolean formula, so it's a formula where there are variables and Boolean operators, so like conjunction and disjunction and negation, is there a satisfying assignment? So can we give each variable a value of true or false such that the full formula evaluates to true? So this, on one hand, this sounds like a very general tool. Like we can see how if we can do this, there are lots of problems we can solve. On the other hand, what is the complexity of this problem? Like is this a tool that's going to be usable in practice? So first of all, first observation we can make is that the satisfiability problem is trivially in NP, right? Because if there is a variable assignment, we can verify it by just evaluating the formula. And we can do this in polynomial time because, you know, we just go over the formula. We have some associative data structure that will give us polynomial time lookup of each variable. And then we go over the formula and we just keep looking up things and we evaluate the, the formula. So it's trivially in NP. But interestingly, it's also NP hard. So this is, of course, not trivial, but it turns out that this problem is as hard as any possible NP problem. In fact, if we just take 3-set, so this is a satisfiability problem that's in conjunctive normal form, which means that it's a conjunction of disjunctions, and each one has at most 3 literals, each clause that we take the disjunction of. So this one, this restricted problem is also NP hard. And in fact, this is quite an important NP hard problem because this is the OG NP complete problem. This is the problem that the original paper that introduced the concept of NP completeness was looking at. So this problem has quite the heritage, I guess you could say. And because it's such a general problem, and because so it's generally useful, but it's also in its full generality quite bad complexity-wise, there are lots of set solvers. So there are mature solvers which are full of all kinds of heuristics to try to speed this up, because like just because a problem is NPR doesn't mean that you can't try to do it as fast as you can for problems that you're actually interested in, right? So you can come up with all kinds of heuristics that will, of course, not be able to give you like a polynomial time solution in all cases, but even just constant time, like we're going to try to actually run this, right? So even the constants matter. So we have these mature tools, and in fact, we have something even better because we have these tools called SMT solvers. So these are satisfiability modulo theories solvers. So these are problems where instead of just having a Boolean formula, we have some other theory that we can refer to. For example, if we have satisfiability modulo integer arithmetic, that means we have a formula where we have Boolean variables, but we also have integer variables, and we can make like Boolean expressions from, let's say, comparing two integers, or we can add integers. So we can say that if x plus, let's say x plus y is greater than z and not q, right? So this is, so here x, y, and z are integer type variables, and q would be a Boolean type variable. And if we pass it to an SMT solver that supports integer arithmetic, then it will tell us whether there's an assignment of both Boolean and integer values such that we can, such that the whole formula evaluates to true. So what we're going to try to do is to represent the full game logic as a Boolean formula, or well, as a Boolean plus maybe other things that are supported by an SMT solver formula. And the inputs are going to be the variables, right? So what we're going to try to do is to take a given game. So, because if you take a given game, then the state will be this horribly big formula of the current input and the previous input and the input before that. And of course, the initial state, but the initial state is not, it's fixed for a given game. And then you have this big formula for the end state. and we want to make the formula which corresponds to this formula's part, which tells us this maybe bool being just true, because if we find a satisfying assignment of variables to this formula by passing it to an SMT solver, then we get the input that wins the game. So that's what we're going to try to do. But the tricky part is that how do we get from this Haskell code that we've written that we can run, how do we get from that to a formula that describes the whole behavior of our reader-writer state monad stack? So this is where we get to symbolic execution. So what we want to do is take a program which refers to inputs that we don't know up front, and we want to get some insight into the behavior of that program such that at the end we can formulate it as an SMT problem. So for example, just for symbolic execution in general, so for example, if we have this expression, right, this program, so what is the value of this? Well, if we know the value of B, then we can just evaluate it, right? If we know that B is true or false, then in both cases we can just do this thing. If we don't know the concrete value of B and X, then we can represent the results symbolically, which basically just means that we take the formula that is we take the program and turn it into a formula by just using symbolic variables for all the variables whose value we don't know, right? So I'm using this $x, $b notation here for these symbolic variables. So then we have this expression. But just because we have symbolic variables inside, that doesn't mean that we can't do any further computation on it, right? So we can make some progress because, for example, we can push in the addition of $x plus into the inner condition. So we get, right? So this plus, we can push it into this condition, giving us this term. And then we can do the same by basically we can then do the comparison, push the comparison under this if as well. So then we get this expression. And the thing is that, so we can do even more, because if we understand numbers well enough to know that x plus 0 is never greater than x plus 1, but on the other hand, x plus 2 is always greater than x plus 1, then even though we don't know the value of x, because x is a symbolic variable, we can simplify it further, and then we get an expression which only has the symbolic variable b inside. So even though we started with a formula that had x and b, we ended up with something that only has b. And then this one, if we, let's say somewhere else in further parts of the code, we say that if this thing is equal to 3, then you win the game, right? Then we just need to satisfy that if b, then 4 as 3 equals 3, which means that b must be false. So if the input to this whole thing is x and b, then a satisfying assignment is one where b is set to 3 and x can be whatever. So we can just pick any value for x. So how are we going to retrofit this into our interactive interpreter? So the heavy lifting is going to be done by this Haskell library called SBV. So SBV is a wonderful library which gives you symbolic versions of some types. So when I say some types, I mean that they have a bunch of types for which they give you symbolic version. So in our case, because we use these int16s, we just replace the current room in the state with a symbolic int16, and also the element types of the item locations array we replace with symbolic int16. Now, of course, the indices don't change because the size of the array will always be based on the number of items in the game, and that doesn't change based on the user input. So that's why the array index remains fixed. So that's why it's an array from int16 to sint16. So we do this change, and then we derive the mergeable type class. So the mergeable type class is a type class that comes from SBV, and that is the type class basically for values which can be symbolically joined. So if you have a branch, for example, because like in this example, right, here 4 and 3, we branch on B here, right, and then on one branch we get the value which is a concrete value, which is 4, and in the other branch we get a concrete value which is 3. But if we want to represent the result of this whole thing as a single symbolic value of type, let's say int, then we need to have a symbolic int which corresponds to if B then 4 as 3, right? So it needs to be both 4 and 3, and moreover it needs to propagate the constraint that is 4-ness or 3-ness depends on B. And this is exactly what this mergeable type class does. So of course sint16 is mergeable because that's the whole point of these symbolic values, that we can combine two sint16s into a single one, and they will carry their like their origin story, if you will, with themselves. So and we can derive it for product types via generic deriving. So that's okay. So that's easy. So now we have changed our state to be symbolic. But so first of all, what does it break, right? Because we had a working program that we could use to play the game, and now we made some change to the definition of some types. So if we try to recompile it, we get some type errors. And that's a good thing, because if we just follow those type errors, we basically get a symbolic interpreter. How? So first of all the operations that use num functions, they will just work because, you know, num is like plus, etc. is overloaded, and there are instances for symbolic versions of number types. So those will just work out. So Boolean operations are somewhat, you know, less fortunate, because the, like, let's say like EQ, okay? So the EQ type class in the Haskell prelude has a method for comparing two values, right? And it takes two A's and returns a bool. Now, if you make the A's symbolic, then of course the result can't be a bool. The result would need to be a symbolic bool. But the EQ class is not overloaded in the whatchamacallit in the return type. So because of that, SBV gives you SBV specific versions. You know, so if you have, let's say, SBVs, like instead of AND for conjunction, right, you have SBV's version of AND, which instead of going from bool to bool to bool, will go from symbolic bool to symbolic bool to symbolic bool. And the SBV's comparison operator, let's say less than, will go from symbolic A to symbolic A to symbolic bool. So you have to just go with your program and basically change all these primitives to, and of course the names are the same, so that they're like they're surrounded by dots, right? So like dot equals equals dot is the SBV version of equals equals. Okay, so that's one thing we need to do. And the other thing we need to do is that we need to make the interpreter monad itself mergeable. Why? Because, okay, so like think of an example where anything that happens inside the game that is conditional on, let's say, being in a given room. And that's probably the easiest example. Like, suppose that if you just have two rooms, if you are in room 1 and you say look, then you get the description of room 1. If you go to room 2 and you do a look, then you get a description of room 2. So obviously the result of the same input, look, will depend on the state, in this case the current room. So if you have some branching inside the engine, then those need to be merged as well. So at first sight, this might look like a daunting task. This might look like a daunting task because, like, we have this point, like, okay, so SBV tells us how to merge symbolic int 16s. Okay, but how does that translate to merging a reader T, writer T state something? Well, the thing is, all the MTL monad transformers are just new types around function types, right? So reader T R MA is just a function from R to MA. Okay, so why is this good? Well, because if you think about merging two values, right? If you want to merge two functions, all that means is that when you get the result from the merged function, you want the result to be the merge of applying the two functions on the same input. So if you have a mergeable instance for A, then you immediately get a mergeable instance from R to A. So that takes care of reader. And we can do the same for writer and state. It's just that in those cases, we have some side conditions that the state has to be mergeable or the writer output has to be mergeable. But if only we have that, we can get mergeable instances for the MTL transformers. Also, we can recover if-then-else syntax by using rebindable syntax language extension. So SBV has this ITE combinator for if-then-else, and we can just rename it to if-then-else. And if we do it with the proper capitalization and turn on rebindable syntax, then that means we can just write Haskell code, which is if something, then something, and it will do the right thing, even if the condition is a symbolic bool instead of a bool. And I see we have a question in chat.
Yeah, I was just going to say if Frederick wants to...
you want to unmute yourself?
Yes, just a second. Can you hear me?
No, okay, in that case, I'll just read up his question. So he's asking if mergeable is similar to semi-group. Sounds like the instance of semi-group M, then semi-group R to M is the same. Well, yeah, I mean, okay. So the thing is that I haven't really told you what the actual method inside the mergeable type class is, right? So the method itself is basically ITE. So if then else. So the primitive is that given an S bool and two A's, you get a third A. So it's like semi-group, except you have this extra symbolic bool which you can't just ignore. You have to somehow carry it around, which in practice will mean that this A type will be made up of other SBV specific types, like a product of them, or a function pointing into them, and so on. Does this answer the question?
Yes, thank you.
Okay, cool, thanks. Okay, so once we have these, we can start, these meaning the mergeable instances for MTL. Then we can start writing mergeable based versions of monadic combinators. So, for example, here's the definition of symbolic when, which is exactly like normal monadic when, except the condition, again, is a symbolic bool. And of course, it will only work if the monad, the action that we are conditionally running is mergeable, because we need to merge the branch where we do something and the one which is just return unit. Similarly, I have found it very useful to make a combinator for pattern matching, because when we run the script, what happens is that we have this static table of which int16 opcode means what action, but the one that we want to run is a symbolic value, because we have computed that based on the user input. We look up the user's input in the table of scripts which maps user input to these script lines, and then that means that after the lookup, the script line itself has become a symbolic value, and then we want to see if it's one of those predefined cases which tells us the semantics of the individual script opcodes. So, and again, we can do that very easily once we have a mergeable instance for the return value, because we just recursively go over the cases and pick the first one. Yeah. So once we have these, so once we have these, we can rewrite everything we had so far. But then we still have one more thing to do, which is that, so that gives us a way of running the interpreter, but we still need to, instead of running it based on the user input, we want to figure out the input, right? We want the SMT solver to drive this process of turn-by-turn interpretation. So if we just take the previous step function and add the symbolicness to it, we have a function which takes us the verb and the noun as symbolic values and gives us a symbolic maybe bool. So of course, so S may be bool, by the way, so it doesn't mean that only the maybiness is symbolic. It means that it's a symbolic maybe of a symbolic bool, right? So it can be symbolically nothing, or it can be symbolically just a symbolic bool. I think it might look a bit confusing, but S maybe is just the type alias for something that wraps both the maybe and the thing inside in a symbolic wrapper. So anyway, so if you have this function, how are we going to run it? So SBMV has a monad called the query monad, where you can do incremental SMT queries of the form, okay, I have this formula, I have this symbolic bool, is it satisfiable? And if not, we can go on. We can take this symbolic bool and we can take everything else that was used to make this symbolic bool and pass it to further symbolic computation. So what we do is I have written this function loop state, which, given a way of producing a single input, so in our case it would be producing a pair of int16s. So these are like fresh ones, right? So we don't really know anything about them. Now, of course, we do know actually something about them. So in the game case, these are not fully unconstrained symbolic variables initially, right? Because we know that they have to be valid words from the dictionary. So we will know that these are int16s that are between 0 and the size of the dictionary, right? Okay, so given a pair of int16s where each is between 0 and, let's say, 20, so this is what we will pass as this guy, and given an initial state, and given a function that for a single input will give us a symbolic bool of whether we are done, will give us a list of inputs. So these are concrete inputs, right? So SBVI means it's a symbolic input. It's a symbolic value. But I is just going to be a normal Haskell type. So in our case, so okay, so when you see S in 16, that's just a type synonym for SBV of in 16, right? So that's just SBV provides these type synonyms to avoid having to write SBV, 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 SBV everywhere. So in our case, we're gonna get a list of in 16 pairs. Concrete values, right? These are going to be the actual words that win the game. And internally, what it does is it applies this function on the first. It calls this to get the first input, which is going to be a symbolic variable constrained somewhat. Pass it to this function, and use run state on it. And this is why I used reader T, writer T state instead of RWS, because the reader and the writer part we can peel off, because the reader part is going to work with the concrete context, right? Because the game data doesn't change. The game data is what we parse the game into. That's not the state. That's the table of scripts and rooms and whatnot. So that's a reader of a concrete value. We can just apply it. Done. The writer part we're going to discard, because to solve the game we don't need to actually look at the output. We don't need to do anything with the messages that would get printed. We're only interested in learning whether we have one or not, and we have arranged things so that we don't need to look at the messages for that, because we find that from the maybe bool result. Okay, and then we turn the maybe bool into, the symbolic maybe bool into a symbolic bool, because at least for the current version, we don't really care if we have lost or not won yet, right? We just want to make, we just accept just true as the true output as the one that we want to get from like that's what we want to satisfy, that the result is just bool. So that's what we turn into a bool. And so when we run this stateful computation, we get the symbolic state which corresponds to the end state after running with the first input, and we get the symbolic bool which corresponds to having won the game. And of course, these share a lot of things between them, because the state and the symbolic bool both depend on details of the game data, details of the initial state, the previous state, and of course, the user input. So if we pass this symbolic bool to the SMT solver and ask it if it's satisfiable or not, and if it tells us that it's not satisfiable, we still have this symbolic state that we can pass to the next round, recursively to loop state, to get the second S-bool, which of course means that we have learned that the game will require at least 2 steps to win. And then if the SMT solver again tells us that it's unsatisfiable, then we do another round, but now we get the third input, because we already know that it is going to take more than 2 inputs. Okay, so, and once we have done this, so we have this solver, but if you think about the source of symbolicness, right? So why do we ever get an end state here and a bool here that has values inside that are not just lifted concrete values? It's only going to be because the user input was symbolic, right? Because the game data is static. That's not going to change. Those are lifted as concrete values. So we have a reader of a concrete value. The writer we can just forget about for a second. And the state, the initial state, before the user does anything, is also going to be full of concrete values, because the initial state is initialized from the game data, because the game data tells us where each item should be and which room we start in, right? So if all the input values are lifted concrete values, so these are concrete int16s that are represented as a symbolic int16 that has only one possible value, then the result and also the output, so the list of strings that we get out, they will have to be concrete values as well. And SBMV has a way of basically going from a symbolic value to a maybe concrete value inside this query monad. So if we feed interactive input as the single possible value of these input variables that we create here. So if we feed in here only values that are lifted concrete values, we can be sure that those maybe concrete values we get at the end are going to be just concrete values. So the nice thing is, not only do we get this checker/solver by minimal changes to the concrete interpreter, we can recover the interactive concrete interpreter from the symbolic one just by getting the concrete values out of the symbolic ones at the end, and of course feeding the concrete interactive input as the input. So that means we can use the same interpreter, the exact same code. And this is, there's no type class magic here, right? So this is not that we managed to write the interpreter generically enough or polymorphically enough that we can instantiate it to concrete or like interactive mode or checking mode. No, no, no. This is really using the exact same interpreter. It's just that on the input side, we lift concrete inputs into symbolic ones, and on the output side, we assert that that all the results and all the output are concrete values. So this is demo time. So I'm not going to show it in real time what it looks like when you run it, because first of all, I can't run it on this machine. So I'm doing the presentation from a crappy Chromebook because I didn't want to install Zoom on anything more precious, and also because we will see it's not that fast. Like I wouldn't want you to wait several minutes for the demo example to be solved. So I'll show you a transcript of it. So the demo game is from ScottKit, which is a modern suite of interpreter, compiler, analyzer, whatever for Scott Adams games. So it comes with a tutorial of increasingly more complicated games. This is the fourth step because it's the first one that is not trivial in the sense that you can't just keep going and do the obvious, like, how should I put it? You can't, like, you have to do things that don't immediately pay off. You have to plan ahead in some sense. But also, it's free of other complications that wouldn't really bring anything new to the table, but they would just require me to implement more of the script interpreter, right? So they basically would add the breadth instead of depth, if that makes sense. So in this game, we have 5 rooms, and the coin is the only treasure, and you won't need to bring it to the throne room, right? So to do that, we have to go through the door, as you can hopefully see. So this is like a log. This represents a locked door. So we have to open the door, but of course, to open the door, we need the key. Unfortunately, the key is in the crypt, where the vampire also is, and the vampire kills the player if he goes to the crypt and lingers around for long enough. But the vampire is afraid of the cross. So if we go to the chamber first, take the cross and carry it with us to the crypt, then the vampire is afraid of the cross. He doesn't dare attack the player, allowing the player to get the key, which can then be brought here to the dungeon to unlock the door so that we can go to the cell, get the coin, and then move back to the throne room. Oh, sorry, this was a spoiler, by the way, because I just spoiled the solution. But I mean, I think you can figure this out yourself. So now the real question is, can Scott check figure this out on its own? And the answer is yes. So it finds a solution of length 14, which I believe is minimal, actually, and it does it in 3.5 minutes. So what you can see from the timing here is that the last step, including building the symbolic representation of the game state and passing it to the SMT solver and solving it, takes about 1 minute, right? Because, yeah, 1 minute. And then we get this 14-step transcript. By the way, I've cheated a bit here. So, of course, in the transcript you would only get 3-letter words, because that's what's in the dictionary, right? Because it maps the words back to the dictionary. I cheated a bit by editing the output to make it more readable by using longer words. But yeah, you get it. That's the only cheating I did. You get the idea. So yeah, like ta-da, it works. So with duct tape and bubble gum, we hacked together something in just 1 week, which was able to solve a small, tiny adventure game. I would say it's a win. And if you look at the timing, we can see very nicely that it's exponential. So this is a log scale on the time, on the y-axis, and in the x-axis we have the number of commands that it have tried so far. So the reason this is exponential is because anytime there's any branching, right, if you just do it fully naively, you get this more and more complex symbolic formula. And basically what separates Scott check from like real solutions to this problem. So what would like I guess the obvious alternative implementation would be to implement this interpreter in Rosetta, which is a Rackit language, or like hash lang in Rackit, that supports symbolic execution. So the idea there is that you write your interpreter in Rosetta and you get a symbolic version of that same interpreter for free, but it does all kinds of simplifications while it's doing the symbolic evaluation to avoid or to reduce rather the blow up. Because of course you can't avoid it, because at some point the reality of MP hardness will hit you, but it avoids it, right? So SBV internally also does simplification, but I don't really have any insight into how well it's suited to this particular use case. So this pattern of having a stateful computation where you just keep turning the crank, and in every step you get these potentially large branches, just to figure out how to process the next input. So what this plot tells, and the last one is faster, right? If you look at the per iteration time, you find that the last iteration is faster, and that's because basically, if the SMT solver finds an assignment, find a satisfying assignment, then that can be potentially faster, right? Because it could be that it gets lucky, or it could be that the heuristics inside the solver lead it down the right path so that it finds the solution quicker than if it has to, then in the case where it has to do more exhaustive search to make sure that there really isn't any satisfying assignment. Like for example, in the penultimate step, right? It still has to go over the possible assignments of inputs based on what it knows about Boolean logic and based on what it knows about integer arithmetic and so on. But that's still, there's still lots of freedom left, and you have to go through those to realize that, let's say, 12 steps is not going to cut it. You can't satisfy it no matter what the 12th command is, and that's why we will keep going and search for a 13th one. And I might be off by one, but whatever, you get the idea. Yeah, so what this plot tells me is that I'm not really keen on putting a real Scott Adams adventure game into the same engine, right? So again, this example is not a published adventure game from back in the days. This is an example adventure for people who want to learn how to write these adventure games in this framework. So it's a much smaller example, but I like, this doesn't make me want to run on larger examples with what I currently have. And that's basically it. And holy crap, it's almost been 1.5 hours. So you can find the code on this URL. It's also, it's on GitHub. I mean, the URL just redirects you to GitHub. And I'd like to give a special thanks to Levent Erkök, who's the maintainer and developer of SBV, because he's been very helpful while I was working on this, because I didn't know the first thing about SBV when I started with this, so I had questions. And also, I found bugs in SBV that he was very quick to fix. So yeah, this work, even though I did the coding of ScotCheck itself, but he was almost as much, he deserves as much credit on the whole thing as I do. And now I guess it's time to check whether the audience is satisfied or not.
Gergő,
so
I just want to say
this is it, and I'm happy to take questions.
Gergő, can you hear me?
Yeah.
Okay, I just want to say thank you very much. That was a lot of fun. Your names are great, ScotCheck, and
well, now I can't hear you. Sorry.
Can you hear me?
Yeah, now I can hear you. Sorry.
Okay, I was just saying your names are great. ScotCheck is hilarious, and it's amazing that you have unsafeperform.io. Some people were mentioning in the chat. I have one question, and then I'll give people a chance to ask further questions in the chat, and I won't keep you too late. I'm just wondering, because this is something that you would clearly do as a kind of intellectual exercise, not because you actually want to create a text adventure game, what do you feel that you learned by going through this process?
Well, I mean, so SBV has been on my radar for a long time because SMT solvers are very much in the zeitgeist at the moment. If you look at, like, last year at ICFP in which was in Berlin, incidentally, you could see that SMT solvers are getting into a lot of places that are like functional programming adjacent or PLT adjacent. So my main motivation was that I wanted to play around with SBV, but I never really had any problems that were a good fit. So then when I saw Martin Lester's talk at WPTE, I knew that this is it, right? Like, so I played text adventure games, I reverse engineered text adventure games, I ported text adventure games to modern platforms, and it's a compiler problem in some sense, it's an interpreter problem in some other sense. This was like a perfect storm of things that like perfect storm of a good opportunity to learn SBV, right? So yeah, that was my main motivation in all this.
Cool. I guess you've not given this talk before, is that right?
Not this. Okay, so I guess I should have started with this in the interest of full disclosure. So after you asked me do this talk, but before I actually did the talk, I was also roped into submitting a extended abstract on a, what's it called, a experience report to IFL. So there, I did like a 20-minute, very condensed version of this at IFL, which is actually on YouTube if anyone wants to watch it. But that doesn't really go into the details of, like, that's basically for an audience that already knows SMT solvers and symbolic execution and all that. So that was really just, okay, here's how I in particular.
Yeah, that was your dress rehearsal for this one.
Yeah.
Well, I think this is a great...
Experience report is basically just academic for, oh, I did a cool thing using an even cooler thing, right?
Get a line on your CV. I think this is a great talk, and you should give it again in the future. And I was going to say travel around with it virtually, I suppose. Were you in Berlin last year?
Yeah.
Okay.
At ICA.
Okay, we probably crossed paths then, because I was also there. And I was in Singapore 2 years ago. How did you end up in Singapore?
I found an interesting opportunity at Standard Chartered. So, but so I know from, like, I go to a lot of meetups, right? And I know that in the audience, I never care about the speaker, and this is like the most boring part of it. So I think we should give people a chance to ask their questions, because they don't care who I am, but they might care about the content of the talk.
Well, I totally care who you are, and also,
yeah, I know, but
I also need to stall a little bit, so if people have questions they can ask. So far I don't see any questions, and it could be sometimes it's an advanced topic and people don't have any questions, or you haven't left any room for questions because you've explained everything.
So I see in the chat the question, I'd like to dive into the translation of model into SMT to storage. So if you go to the GitHub repo, which is redirected from the unsafe perform IO URL that I have on the last slide. So if you look at the repo, in the commit history, there's a particular commit that is just the switch over from the concrete original, how do you say it, idiomatic Haskell interpreter to the symbolic one. So there's like one particular commit where the magic happens, if you will. And then, of course, there are lots of later commits which make things nicer or make things faster by making the branching factor smaller and so on. But there's one commit that should show you, the change needed to go from concrete to symbolic. But it really, like, if you want to do it yourself, I really recommend what I did, which is to just change the types of your state to be symbolic, and then just let GHC tell you what need to change, because you will get a lot of type errors saying, oh, this has type int, but I want a symbolic int, or this has type symbolic int, but I want an int. And you look at those places and you figure out what you need to do there. Maybe it's as simple as putting a dot on both sides of an operator name. Maybe it's trickier, like how I had to add mergeable instances for MTL transformers. But ultimately, GHC will hold your hand and help you.
Can we get a link to your slides, or maybe you can email it to me and I will post it later?
Yeah, so the slides are, I haven't uploaded them yet, but tomorrow I'm going to upload them, so they're going to be on unsafeperform.io. I just love using this URL. I pass up an opportunity to say the URL.
Yeah, I mean, I would too. Well, I don't see any other questions, and it is late, so shall we call it a night then?
Sure. Thanks for having me. And yeah, I really hope that the silence is not a stunned silence of what on earth was this guy babbling about.
I don't think so at all. I think this was a fantastic talk, and yep, you're getting lots of kudos in the chat. I think people are just really interested in the topic. Maybe they don't know a lot about SMT solvers, but I think this is a very fun way to present the information. And I mean, I'm probably going to have to watch it again to absorb all of it, but really great stuff. Thank you so much for bringing it to us.
Okay, cool. Yeah, thanks for having me. And I try to attend these virtual meetups if the time zones permitting. We'll see.
Well, you're always welcome, and hope to see you again someday in Berlin or Singapore or Hungary or wherever.